Hi everyone. Today we are going to explore one of the most fascinating discoveries in modern physics, that is the photoelectric effect. Before we start the photoelectric effect, let's understand the Planck's quantum theory, the key idea that led to the concept of photons. According to this Planck's quantum theory, light consists of small packets called photons or quanta. We can also say like this: light is a form of energy. The energy is available in the small packets are called photons or quanta. So each photon carries a specific amount of energy. So we know light is present having different colors. Okay, red light, green light, blue light, yellow light, orange light, like this. So it means that we have different photons also, so different energies also. Okay, so we have taken the red photon means from the red light. Okay, it is having the frequency, it is having the wavelength, it is having the energy. Okay, so the energy of the photon we can get it by two formulas. One formula is E is equal to hf, another formula E equal to hc by lambda. What is h? H is the Planck's constant. Its value is around 6.626 times 10 to the power of minus 34 joule second. So sometimes we take it 6.626 as 6.63. Okay, so f is the frequency, SI unit is hertz. Okay, one interesting thing is, if the photon is having the more frequency, high frequency means high energy, so the relationship between the frequency and energy is direct relationship. So let's discuss another formula, E equal to hc by lambda. So lambda is the wavelength, SI unit is meters. Here the c in this formula means the speed of the light, which is equal to 3 into 10 to the power of 8 meter per second. Okay, the relationship between the energy and the lambda is inverse relationship. It means if the photon have the wavelength longer, okay, longer wavelength photon will have the less amount of energy in it. So inverse relationship. Okay, now let's come back to the red photon. So frequency is 4.3 times 10 to the power of 14 hertz. Wavelength is around 700 nanometers. Okay, let's calculate its energy. Okay, either hf or hc by lambda. So E equal to hf formula is used. The energy is 2.85 times 10 to the power of minus 19 joule. So remember, 10 to the power of minus 19 joule, it means that the energy is very small in joules. Yes, obviously in atomic and in quantum physics the energy values we get in joules will be very small. So that's why we use the more convenient unit we use for the energy, that is the electron volt. Of course, electron volt is not the SI unit, only joule is the unit, SI unit for the energy. So let's discuss how to convert the joule into the electron volt. Very simple, just divide the joule with 1.6 times 10 to the power of minus 19. That's it. So this is the answer for in terms of electron volt for this red photon. So another unit also, another conversion, that is from electron volt to the joule conversion. It's simple, very simple. 1 electron volt equal to 1.6 times 10 to the power of minus 19 joule. Sometimes our values are given in electron volt, so but whenever we use this formula or this formula, so energy should be in joule. So then we have to convert. Very simple. So 1 electron volt equal to 1.6 times 10 to the power of minus 19 joule. 2 electron volt means 2 times 1.6 into 10 to the power of minus 19 joules, like this. So multiply with 1.6 times 10 to the power of minus 19. Okay, now let's discuss our favorite, that is the photoelectric effect. So it is the emission of electrons from a metal surface when exposed to light of suitable frequency. And these emitted electrons are called photoelectrons. So very clear, the name itself, photo means light, electric means electrons, that's it. So we are getting the electrons from the light, that is the photoelectric effect. Okay, let's understand this. So a metal surface, or say a metal is taken, the potassium metal is taken here. So some parameters are given here. The threshold frequency of this potassium metal is 4.83 times 10 to the power of 14 Hz, whereas the work function is 2 electron volt or 3.2 times 10 to the power of minus 19 joule. This is about the potassium metal. Okay, let's first discuss the work function. Work function means it is the minimum amount of energy required to remove an electron from the surface of a metal. So for this potassium metal, the work function is 2 electron volt. It means that if we supply an energy of 2 electron volt or more than 2 electron volt, we can get the electron from the surface. That's it. Okay, let's discuss here. Suppose the energy of the photon is equal to 1.78 electron volt, whereas the work function of this metal is 2 electron volt. It means this photon is unable to eject any electron from this metal surface because energy of the photon is less than the work function of this metal. So no electrons. Okay, we can also discuss the same thing in terms of the frequency, that is the threshold frequency. Okay, so the threshold frequency for this metal, potassium metal, is 4.83 times 10 to the power of 14 Hz, whereas the frequency of this red photon is 4.3 times 10 to the power of 14. So we need 4.83. So whereas this one is 4.3. So it means the frequency of this photon is less than the threshold frequency required. So less than the threshold frequency F0. It is sometimes it is also called cutoff frequency FC. Okay, we can also discuss the same concept in terms of the wavelength lambda, also cutoff wavelength. Okay, so I hope you got it. Let's move on to another example. This time we have taken the green photon. The green photon is having an energy around 2.25 electron volt, whereas the work function of this metal is 2. So it means now the energy of this photon is more than the work function of the metal. So more than the work function means we can easily eject the electron. So we call this electron as the photoelectron. Okay, now this photon, remember here, the fundamental principle in this photoelectric effect is only one photon can eject only one electron. It means, for example, here the work function is 2 electron volt, whereas the energy of the photon, for example, energy of the photon is 4 electron volt. Okay, so work function is 2. So it means that this one photon cannot eject 2 electrons. Of course it is having the more energy, but no, one photon can eject only one electron. So where the remaining energy will go, the extra energy it is having, so that remaining energy will be in the form of kinetic energy. It remain with the photoelectrons. Okay, let's discuss again. So energy of this green photon is 2.25 electron volt, whereas the work function of the metal is 2 electron volt. So okay, electrons are ejected, electron is ejected. Okay, whatever the extra, that is 0.25 electron volt energy, will remain with this photoelectron in the form of kinetic energy. So once we know kinetic energy, so we can say it is having the speed. So we can also write in terms of the speed also, that is, so here the maximum speed is 2.96 times 10 to the power of 5 meter per second. How we got this? The very simple. So we know the formula, kinetic energy equal to half mv square. This is the formula. So from this we can write V equal to root 2 ke kinetic energy by m. This is the formula we can use. So it means we need the mass of the electron here. Without this we cannot find. It's around 9.1 10 to the power of minus 31 kg. Okay, remember one thing, directly you cannot use electron volt in this kinetic energy. We cannot use, it's wrong. Okay, so convert it to the joule, that is 0.25 10 to the power 1.6 10 to the power of minus 19 joule. So this number we can plug it in this kinetic energy. So like this we can find the speed of the ejected electrons. Okay, this is we discuss in terms of the energy work function like this. Okay, we can also discuss in terms of the frequency also. So look at here, what is the frequency, the cutoff frequency or the threshold frequency here for this potassium metal, that is 4.83 10 to the power of minus 14 hertz, whereas the frequency of this photon, the green photon, is 5.5. so this is 4. So this is the frequency is more than the cutoff, so that's why it can able to eject the electron. Okay, so the frequency of the photon should be more than the cutoff threshold frequency. Another example. Okay, so here the extra energy whatever I discussed, this is all because of this Einstein's photoelectric equation. So Einstein's photoelectric equation is energy of the electron is equal to work function of the metal plus kinetic energy of the photoelectron. Okay, I repeat, this energy of the photon is equal to work function of the metal plus the kinetic energy of the photoelectron. So from this we can write, okay, kinetic energy, how we got this answer, kinetic energy equal to the energy of the photon minus the work function. So that is 2.25 minus the work function 0.25, which is equal to 0.25 electron volt. Let's take another example. This time we have taken the blue photon. So the energy of this blue photon is around 2.62 electron volt, whereas the work function of this metal is 2 electron volt. That's it. Yes, it is able to eject the electron, because the energy of the photon is more than the work function. Okay, the remaining extra energy, that is 0.62, it is remained with the photoelectron in the form of kinetic energy. So this time the photoelectron has the more kinetic energy, it means it has the more speed compared to the previous one. Okay, so we can also discuss in terms of the frequency. Here the frequency of the incident photon is 6.3 10 to the power of 14 hertz, whereas the threshold frequency required is 4.83. so that is the reason it can able to eject the electrons. This is the photoelectric effect. Now let's study the photoelectric effect in terms of intensity. Intensity determines the number of photons per second. When the light of certain frequency shines on a metal surface, it can eject electrons only if the frequency is above the threshold frequency. Now let's see. Here the intensity of the light is more compared to our previous discussion. There only one photon. Here many photons are there. Let's take the 4 photons are here. Okay, but each photon have the same energy, each photon have the same frequency, each photon have the same wavelength. But here all the photons have the frequencies less than the threshold frequency. All the photons have the energies less than the work functions. So none of the photons can able to eject the electrons. Of course, more number of photons are here, that is more intensity is there, but no use, no electrons are emitted. But if the frequency is above the threshold, so here every photon has the frequency more than the threshold frequency, or you can say the energy of every photon is more than the work function here. So it means they all can eject the electrons. For example, here 4 photons are given, they can eject the 4 electrons. So here increasing the intensity will increase the photons, that's it. So if the frequency is above the threshold frequency, then one photon can eject 1 electron, 2 photons can eject 2 electrons, 3 photons can eject 3 electrons, like this one. But the maximum kinetic energy of the emitted electrons remains the same, all have the same kinetic energy. So increasing intensity will increase the more number of photoelectrons, that's it. It will not increase the kinetic energy. Let's do some numerical problems based on what we have discussed so far. Before that, let's write the formulas. First start with the photon, then metal, then photoelectron, last one Einstein's equation. Photon, the energy of the photon is equal to hc by lambda or hf. Metal, the work function of the metal, phi equal to hc by lambda naught. Lambda naught is the cutoff wavelength, hf naught, f naught is the cutoff frequency. For the electron, we have the kinetic energy of the electron, that is equal to half mv square. Einstein's equations gives the relationship between the photon energy, the work function of the metal, and the electron, all the three. Okay, that is E equal to phi plus K. Okay, remember, whenever we are using these formulas, especially these formulas, we have to keep the energy in the joule, must. So we need to, sometimes electron volt will be given, so let's see the conversions here. 1 joule equal to 1 divided by 1.6 times 10 to the power of minus 19 electron volt. This is one conversion. Another conversion is 1 electron volt is equal to 1.6 times 10 to the power of minus 19 joule. This is another conversion. Okay, about the Einstein's equation, we can keep it either the fully, all the values, either it should be in all the values, either it should be in joule or it should be in, all the values should be in electron volt, that's it. Whereas here individual formulas, it should be only in. Let's start the problems. Problem number 1. A sodium surface is illuminated with a light of wavelength. Wavelength is given to us. Light means the photon. Okay, otherwise you can write it as the light here also. Okay, a wavelength 0.3 micro means 10 to the power of minus 6 meter. The work function for the sodium is 2.46 electron volt. So work function means 2.46 we may require the joules, so convert it 1.6 into 10 to the power of minus 19. We have to multiply with, that's it. Come on, calculate the energy of the photon. Energy of the photon means hc by lambda or hf. So wavelength is given, so E equal to hc by lambda is the best one. So that is equal to 6.63 times 10 to the power of minus 34 times the c, 3 into 10 to the power of 8 over the lambda. Given value is 0.3 times 10 to the power of minus 6. The answer is 6.63 times 10 to the power of minus 19 joule. That's it. Next one, the B bit. The maximum kinetic energy of the ejected electrons. So it's up to us. We can also, here in the previous one, we can also convert the joule into the electron volt. That is 6.63 times 10 to the power of minus 19 over 1.6 into 10 to the power of minus 19. The answer is 4.14 electron volt. The B bit. The maximum kinetic energy of the ejected photoelectrons. The maximum kinetic energy we have to find. So either we can use this one, but the speed is not given, so we use the Einstein's kinetic equation we can use. So maximum kinetic energy means kinetic energy we can get it by energy of the photon minus the work function. So energy of the photon, so 4.14. I am keeping everything in the electron volts, it's very convenient. The work function is given as 2.46, so which is equal to subtract 1.68 electron volt. The third one, cutoff wavelength for the sodium. Cutoff wavelength of the sodium means from the work function. So cutoff wavelength means lambda naught we have to find. So hc by work function is equal to hc by lambda naught. So from this we can find the cutoff wavelength lambda naught equal to hc by the work function. So h is 6.63 times 10 to the power of minus 34, the c 3 times 10 to the power of 8 over the work function in the joule, that is 2.46 times 1.6 into 10 to the power of minus 19. The answer is 5 times 10 to the power of minus 7 meters. These are the answers. Next problem. What minimum frequency light means what minimum frequency light will eject photoelectrons from copper surface? Minimum frequency means f naught, cutoff frequency we have to calculate. So nothing is given, so we can only solve if the wave work function of the copper is given. So the work function of the copper is around 4.7 electron volt. Now we can calculate. So work function, the formula is hf naught. So from this, f naught value is equal to work function in the joule divided by the h. So work function in the joule, that is 4.7 times 1.6 into 10 to the power of minus 19 over the h value, that is 6.63 times 10 to the power of minus 34. The answer is 1.13 times 10 to the power of 15 Hz. 1.13. This is A, the B one. If this frequency is tripled, if this frequency is tripled, find the maximum kinetic energy in the electron volt of the resulting photoelectrons. Maximum kinetic energy, velocity is not given, so we use the Einstein's equations. So I want to write directly. Maximum kinetic energy, the formula is energy of the photon minus the work function. So energy of the photon is not given, so the formula is hf. So it's given the frequency is tripled, so 3 times the previous one, hf naught minus the 5. So plug in all the values. H is 6.63 times 10 to the power of minus 34 times 3 times frequency 1.13 times 10 to the power of 15. This whole thing minus the work function in the joule, that is 4.7 times 1.6 into 10 to the power of minus 19. Use the calculator and find the answer. The answer is around 1.5 times 10 to the power of minus 18 joule. But they are asking find the answer in electron volts. So just divide the number, that 1.5 times 10 to the power of minus 18 divide with charge of an electron, that is 1.6 into 10 to the power of minus 19. The answer is 9.4 electron volt. Another problem. Electrons are ejected from a metallic surface with a speed ranging up to 4.6 times 10 to the power of 5 meter per second. The speed is given to us when the light, so this is related to photon, okay, when the light with a wavelength of 625 nanometers is used. What is the work function of the surface? Work function of the surface. Work function, the formula is hf naught or hc by lambda naught. So in this case, what is the work function? This is for the photon 625. So this formula is not useful for us now. No. So let's use the work function from the Einstein's equation, that is the work function equal to energy of the photon minus the kinetic energy. We will use this one. So energy hf minus half mv square. So hf h is 6.63 times 10 to the power of minus 34. The frequency, the frequency is not given again, sorry. So I will change, instead of hf we will use hc by lambda, that is better, hc by lambda. So that is equal to 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 over the lambda given 625 nano means 10 to the power of minus 9, that's it, minus half mv square, half the mass of the electron. Please remember the mass of the electron should be given, otherwise very difficult to solve this problem. 9.1 times 10 to the power of minus 31, this is the mass of the electron, time the velocity, the speed of the electron, that is 4.6 into 10 to the power of minus 5, the speed square. Use the calculator, so you will get the answer around 2.2 times 10 to the power of minus 19 joule. If you want, you can convert the work function into the electron volt just by dividing with 1.6 into 10 to the power of minus 19. The answer is 1.4 electron volt. A part is over. Let's calculate the B one. What is the cutoff frequency? Cutoff frequency means the f naught we have to calculate. Now we use this formula h f naught. So from this, f naught equal to phi by h. So phi, the work function, it should be in the joule. only this is allowed in this formula, that is 2.2 times 10 to the power of minus 19 divided by the h, that is 6.63 times 10 to the power of minus 34. The frequency is around 3.3 times 10 to the power of 14 Hz. This is the answer. Last problem. Molybdenum has a work function of 4.2 electron volt. So 4.2 electron volt converted to the joule may be useful, 1.6 into 10 to the power of minus 19. So this is in the joule. Okay, that's good. Find the cutoff wavelength lambda naught, and also the threshold frequency, the f naught we have to find for the photoelectric effect. So we know the formula, work function equal to hc by lambda, one formula, another formula, work function equal to hf naught, so which is equal to, so let's rewrite the lambda naught from this equal to hc by the work function. Okay, 6.63 times 10 to the power of minus 34 times 3 times 10 to the power of 8 divided by the work function in the joule, that is 4.2 times 1.6 times 10 to the power of minus 19. So the lambda is around 2.96 times 10 to the power of minus 7 meter. This is the cutoff. So in some books you find the cutoff with lambda naught, some books lambda c. Okay, now the frequency, cutoff frequency or threshold frequency, the formula is f naught equal to the work function in the joule divided by the h. Work function in the joule is 4.2 times 1.6 into 10 to the power of minus 19 over the h, that is 6.63 times 10 to the power of minus 34. The answer is 1.01 times 10 to the power of 15 Hz. That's it. Thank you very much.